over these couple of homework problems. My apologies. But all the notes are still there, so like, it is what it is. I made a boo-boo. So, continuing with section 1.7. So where we left off last time, we had just talked about function composition, run through a couple of examples, and pointed out that function composition is not commutative. By that we meant that f composed g of x was not equal to g composed f of x. Does that sound right to you guys? Okay. So let's kind of continue forward. So we'll go ahead and do another definition here. So we say that two functions f and g and we say then that g is the inverse function of f if and only if g compose f of x is equal to, f compose g of x equals g compose f of x, which equals x. Basically what this is saying is that if I take some input x, and then I do f to that input, get an answer, and then do g to that answer, I should get back the original input. Or if I do the reverse order, where I do g to the original input, take that answer, and then do f to the answer, again, I should get back the original input. Is everybody okay with that? So basically what it means is that, like, g needs to undo whatever f did to give you back your original input, and then vice versa. F would need to undo everything that g does to give you the original input again. So when we talk about these inverses, then it's basically just a way of recovering the original input, right? So if we take a look at like a mapping diagram, this mapping diagram represents some function f, right? If I observe that function f, what I see is that 1 is mapping to 4, 2 is mapping to 6, and 3 is mapping to 5. If I wanted the inverse for this function, I want a function that undoes whatever f did. So, my domain here should be the outputs from f, and my range should be the inputs from f. And instead of 1 going to 4 for f inverse, I want 4 to go back to 1. I want 5 to go back to 3, and I want 6 to go back to 2. And this would be my inverse. We called that, or we use the symbol f to the negative 1 to represent f inverse. Remember that f is a function, so that exponent on a function doesn't mean the same thing that an exponent on like a number or a variable would mean. So it's just a different use for that notation. Everybody's okay? So f to the negative 1 doesn't mean 1 over f. Everybody's good? Okay. Note here that f inverse in this case is a function, right? What if instead we had a function that was a set of ordered pairs? So here we'll just describe this function as a set of ordered pairs. So in f, negative 2 goes to 4, negative 1 goes to 6, 3 goes to 8, and then 5 goes to 8. If I want the inverse, I need to reverse the directions. So instead of negative 2 going to 4, I need 4 to go back to negative 2. I would need 6 to go to negative 1, 8 to go to 3, and then 8 to go to 5. What do you notice about this? It's not a function. Why not? Yeah, because the input of 8 has 2 different outputs. Everybody happy with that? So one of the things that we'd like to develop here is a criteria on how we can determine whether these inverses will be a function or not. So do we actually have to find the inverse and then look at it and decide if it's a function? No, what we'd prefer is to just be able to look at our original function f, and before we even go about trying to find the inverse, to know whether that will be a function or not. Everybody's okay with that idea? So on our way to developing a method to do that, we're going to make some new definitions. So the first one is the term onto. And an alternative term for onto is surjective. It's probably the less frequently used of the term for onto, but still quite common. So we say that a function is considered onto if every element in the range is mapped to by some element in the domain. And we'll do some examples of these vocabulary in a moment. I'm just going to give you all the vocabulary first. Just because I can do multiple, or I can do an example for all of the vocabulary with like the same example. It just makes it a little bit easier. Oh, goodness. The next one is the term 1-to-1. And the alternative for that is injective again. The less frequent, but still quite common, so we say a function is considered 1-to-1 if every element in the domain maps uniquely to distinct elements in the range, and then lastly, we say a function is considered bijective. Make that neater. If it is both 1-to-1 and onto. Okay, so let's look at some examples here. Here's a function f. Is this function onto? No, why not? We have some ranges that we didn't use, right? So because we have a range that wasn't used, we can say that this function is not onto. Everybody feel okay with that? Is this function 1-to-1? No. Why not? No. We have a range value that's used more than once. Is everybody okay with that? Let's kind of do the same thing, but this time maybe we'll look at a graph. Is this onto? It's not, because we have some y coordinates that aren't used. Is it 1-to-1? Nope. because we have some y coordinates that are used twice. Does that feel okay? So what does something that's one-to-one and onto look like? Well, have something really silly like this. That's one-to-one and onto. All the y coordinates are used, right? And no y coordinates are used more than once. Can I be one-to-one and not onto? Sure. What if we just have something like that, like a ray? Lots of y's that aren't used, but every y that is used only one time. Can I have something that's onto but not one-to-one? Sure. How about something like this? All the y coordinates are used, but some of them are used more than once. Does that feel okay? It's a little bit easier once we kind of can start just drawing graphs to give you examples of things that are one but not the other. Okay. So what if we have like a graph and we want to give the inverse? This is my suggestion. I think the easiest way to do this is I'm going to identify like a couple of points on this graph. So let's say this one, let's estimate this maybe is 0, 2. And maybe we estimate this one as like 3, 0. And then maybe this one is like 4, 4. What's up? Yeah, thank you. Negative 4, 4. Okay, so we just identified a couple of points on our function. Now, to create its inverse, what I'm going to do is I'm going to swap the x and y coordinates like we were doing before. So 0, 2 becomes the point 2, 0. 3, 0 becomes the point 0, 3. You better believe it. Goodness gracious. Not that I don't know how to do this, it just, you make mistakes, guys. I would have come up with it eventually. Thank you. Okay. And then negative 4 so then I have 4, negative 4 is my last point, right? You guys agree with that? So the important piece is that this guy was my vertex before. It's still my vertex now. So I'm just going to kind of connect this. Is that okay with everybody? I did kind of a poor job drawing that. It's maybe a little better. I don't know. Does it feel okay? What can we say about this inverse? Not a function. If I look at f, what else was f not? It's not one-to-one. It's also not onto. Which one of those is going to be the more important one for determining if it's a function? Which part of us ran? Which of those caused the problem when we drew our inverse? The one-to-one part, right? This is really our predictor. So let's think about what it means to be not one-to-one. That means that some y-coordinate is used by two different x-coordinates, right? Everybody agree? So when I swap the x's and y's for my inverse, that means those two, that y-coordinate that was used twice in f becomes an x-coordinate being used twice in f inverse. Everybody agree with that? So immediately I can tell that, like, if f is not one-to-one, then f inverse is not a function. Keep in mind that I did not write this as an if and only if. Is it possible to come up with a function that is one-to-one whose inverse is not a function? Well, I don't know, right? We didn't write it that way, but it's not, I didn't write it as an if and only if. We're not saying that the reverse is also true, that if the function is one-to-one, we're always going to have the inverse would always be a function also. We're not saying that with this statement. Is everybody okay with that reasoning? Or that distinction anyways? Okay. So another observation I can make here is if I come through and I draw this line, y equals x, what we should be seeing, and I guess I was a little off when I drew this green piece here. Let me try it one more time. There we go. Is that f and f inverse should be reflections across this line, y equals x. So like if I take this part of f and I reflect it across that blue line, y equals x, I get like that part of f inverse, right? If I take like this, this part of f and reflect it across that blue line, I get like that piece of f inverse. And similarly, if I take this part of f and reflect it across y equals x, I get like that part of f inverse. You guys kind of see that? So that's another way of like drawing the graph of an inverse, is you can draw on that line y equals x and try to draw those reflections. I find that a little bit more challenging than just assigning a few points to f of x and then like transposing the coordinates and then plotting that and connecting it. You guys agree with that? I think that just making the points is easier, providing you don't screw up whether the signs are positive or negative, which apparently I was having a problem with this morning. I would have figured it out eventually when I drew the graph, and it was like, that is not the reflection of this thing. What did I do wrong? Is everybody okay though? So you can really draw your inverse for a graph either way, either with points or by using a reflection, whatever you're more comfortable with, whatever you think is going to be more expedient for you. Either way of doing it is fine. So we have this. And visually, if I'm looking at a function, what's the easiest way to tell if that function is one-to-one? Yeah. So if you remember, to check if something's a function, we use a vertical line test. That vertical line test is basically just checking for repeated x's. If I want to check if you are one-to-one, I'm going to use a horizontal line test. Because I know that horizontal line tests will check for repeated y's. And repeated y's means that something is, or that function is not one-to-one. Everybody happy with that? Okay. So we've talked about how to find inverses if you have like a mapping diagram. That was easy. Basically, we just flip the directions of everything, right? Talked about finding inverses if you have a set of ordered pairs. You can just transpose the coordinates. Talked about finding inverses if you have a graph. What if we have something written with like a function notation? So what if I want to find the inverse of like 3x minus 7? So the first thing I like to do is I'm going to replace the function notation with just a y. And then I'm going to isolate the x, just using algebra. So in this case, we would add 7 to both sides. And then divide by 3. Once I've isolated my x, I would then swap the x and y coordinate. And basically we're finished then. We would say f inverse is equal to x plus 7 all over 3. Or you could write it as x over 3 plus 7 over 3 if you want. That's fine too. Let's do another example of this that's a tad more challenging algebraically. Sound good to you guys? That one was probably kind of trivial for us. This one should be a bit more challenging. Oops. So let's say we have g of x equals 2x plus 5 over 5x minus 8. So my first step, I'm just going to replace the function notation with a y. And now I want to isolate the x. What do you notice that's different about this problem than the previous one? There's a big difference. It's more than one x, right? So, to isolate the x, we're going to need to get that x that's in two different places just into one place. That's going to be kind of my goal. I'm going to start by just like cross multiplying here. Oops. To get rid of the fraction. Everybody's good with that? Let's distribute the y through. And I'm going to get the stuff with y's in it on one side and the stuff without the y's on it onto the other. So I'm going to subtract 5xy from both sides and subtract 5 from both sides. Everybody still doing good? Now if I look at the left-hand side, there's a greatest common factor of x on the left-hand side. So I'm going to factor that greatest common factor of x off. And that has gone and changed from having x's in two places to having x in just one place. Everybody see that? Sneaky, sneaky. I can then divide both sides by 2 minus 5y. And then swap my x and y coordinates. And I would say here, I would do some more simplifying because I can like goose out of here a negative. So I can write that as 8x plus 5 over 5x minus 2. If I just multiply the top and bottom by -1, I can get rid of a bunch of negative signs there and make the problem just a little bit simpler. That's the way that I would write it. It's not wrong the way it was written before, but I don't know. Like if I can get rid of some negative signs, like let's get rid of those negative signs. You've already seen that I forgot to write them down half the time when I was writing down those points before. You know, just one less thing for me to forget. I'm trying to have some fun, you know. We okay with that, though? A tad bit more challenging algebraically, although the process was still identical, right? Isolate the x, then swap the x and y's. You know what I mean? Excuse me. Okay. Let's do another. What if we have A, B, F, G, H would be what we're on now? So we'll do the same thing. Replace the function notation with just a y. And then go about isolating that x. So add 4 over. Divide the 3 over. Square root both sides. Remember, when we square root both sides of an equation, that creates a plus or minus. And then swap my x and y's. What do you notice here about this inverse? Oh, come on, guys. What do you notice about this inverse? It's not a function, is it? Why isn't it a function? Because of the plus or minus, right? So one thing we might want to do is we may want to restrict the domain on our original function so that when we create our inverse, it would be a function. So if I think back to my original, if I graph 3x squared minus 4, it's going to look something like this, where it has a vertex of 0, -4. So I could restrict its domain by taking just the parts of it that are either greater than 0 or just the part whose x-coordinates are greater than 0. Or I could take just the part whose y-coordinates are less than 0. Either would be okay, because by taking just that part of the domain, if I chop everything else off, I now have something that's 1-to-1, right? If I lose 1/2 of that parabola, everybody see that? So just for the sake of argument, let's say that we keep only this half. So if I add in the restriction that x has to be greater than or equal to 0, if I get to this step, it allows me to drop the minus from the plus or minus, because I know that x has to be greater than or equal to 0, so it can't ever be negative. It allows me to drop the negative there. which then would imply that h of x is just this, which would be a function. So depending on what the directions are, whether they give you a restriction on the domain or they ask you to write the inverse function as opposed to just the inverse, you may need to restrict a domain or not, depending on what the directions say. Are we okay there? Okay. Another one. I know you guys are like, are you serious? And it's like, well, yeah, A, B, C, D, F, G, H, I would be, yes, sir. Absolutely. So let's say we have the function is the square root of 12x plus 5. Start the same way. Rewrite the function notation with a y. What would I want to do then? How am I going to get rid of that square root? Just shout it out if you know. Square both sides. So it's going to give me y squared equals 12x plus 5. And then what would we do? Subtract the 5. Very good. And then divide by 12. Great. And then when we swap our variables and whatnot, we have our inverse function. So I merged some steps there at the end after doing a bunch of these examples. Is that okay? Where I swapped the x and y and wrote the inverse all in the same step. You guys see that, right? Okay. Let's get a little bit trickier now, yet. Let's see, J. I'm doing this because what you haven't realized maybe yet is that we're going to go ahead and review all the different function types that we saw in our Algebra 2 class last year. So we've done like a quadratic, a square root function, a linear function, a irrational function. Here's an exponential function. Okay, so let's just replace the function notation with a y. What's my first step here? Anybody? We're trying to get the x by itself. Any ideas? Wrong answers are okay. You don't have to know the right answer. They can just be ideas. Okay. I would not want to do that. And that's okay. Like, I'm glad that somebody's at least asking, because this, again, like, I don't expect you to remember exactly how to do these things, right? Yes, this was something we did last year, but I don't expect you to remember right away. I want to, but as we like make suggestions of things not to do, which are probably our first ideas, I want to review like why that won't work, right? So 3 is the base of an exponential, right? So dividing by 3 is not going to cancel the 3. Margot.
Can you multiply like 2?
Yeah, let's multiply both sides by -2. That'll get the fraction out of there. That's a good idea. That would be the first thing I would do. Now we got to get rid of the 3, right? And we've already suggested dividing by 3, and I already poo-pooed that suggestion, which again is the natural first thing that students everywhere suggest on this problem. Do you remember how to get rid of an exponent base of 3? We did this last year. Yes. No.
You know what? You know what I'm thinking of? Like,
maybe Alyssa? Yes. To cancel an exponent base, we need to use a logarithm. The specific logarithm that we want to use is log base 3 so that it matches the exponent base on our exponential. Grace, I think you were thinking of exponent, like a rational exponent as opposed to a, like if it was x to the 4/3 or something, then you would use an exponent reciprocal there, I think is what you were thinking of. Not positive, but I think that's what you were driving at. Right? Do we remember kind of doing this last year? We'll do logs again at the end of the year also, but ideally, we remember this. So far, so good? Okay. Last step would be then to divide by 4. That's fine. I'm going to write it as like 1/4 times. So I think it's a little bit more clear what's going on, but it wouldn't be wrong to put that stuff all over 4. In my experience, students have sometimes a habit of taking like everything over 4 and just ending up with like the stuff inside the logarithm over 4, which is definitely not the same thing. And then we can swap our x and y and write our inverse. And I'll state for the record, you could have cleaned this up a little bit more, but I'm not too worried about that part. That would be getting pretty deep into our properties of logs that I don't really want to get into that right now. Again, because at this point, I'm guessing most of us don't remember those anyways, and it'd be like we're reteaching a whole thing that I plan on doing later on in second semester anyway, so we're just not going to do it now. You know what I mean? One more. What are we at? K, right? So let's say we have k of x equals 5/3 the natural log of 7x minus 1. Remember, ln is the abbreviation for the natural log. Well, we'll replace the function notation with a y. And what to do next? Again, we're trying to get the x by itself. Give you a hint. We got to get rid of that 5/3. Good. That was easy. I'm sure you would have come up with that in just another second or two by yourself. You probably just weren't sure if that was the first thing you needed to do or not. Okay. What's the next thing we need to do? Got to get rid of the ln there, right? That natural log, Alyssa? Yeah, so to get rid of a logarithm, we're going to use an exponent base. The base of the exponent should match the base of our logarithm. We remember that the base of the natural log is e. So I'll do exponent base e to both sides. That's why I drew the e so big. It's just to make clear that we're not multiplying by e. Everybody's okay with that? Hopefully this feels like, oh yeah, like this stuff. I kind of remember doing this. If I was your teacher, I really expect you to remember doing this because we did this, and I thought we did quite a thorough job doing this. Okay, what do we do from here? To finish this guy out. Well, not till I've added 1, though, right? Yeah, let's add the 1 first, and then we'll divide by... Sure. And that's probably just the way I would write it, is something that looks like that. Seems the easiest. So when I switch my exponent, or switch my variables, and write this as a function, there we are. Everybody's good? So we found these inverses algebraically. How do you know you're right? How do I know that, like, okay, I got this answer. Is this answer actually correct? Well, you could go all the way back to our definition of an inverse. Since this is an if and only if definition, we can use this to prove that the two things are actually inverses if we can demonstrate this. Yes, of course. So, which example do you want to use? F through K. I'm going to use F, G, H, I, J, K. Anybody with a preference? G, that's a good one because I think it's maybe the worst one. Oh, G. Yeah, G. G is the rational one, right? Yeah, that one's nasty. Let's do it. How did you know it was going to be the bad one? Oh, that was sweet. So if I want to verify these two things are inverses, I need to do two things. I need to do G compose G inverse of X and show that that gives me X. And then I need to do G inverse compose G of X and also show that that gives me X. So the first one is just by definition, g of g inverse of x. So I'm going to replace g with g inverse. I'm going to replace with the function that we found. Everybody's okay there? And then that's going to tell me I'm going to need to plug that expression in for the x's in G. Everybody okay with how I've done that? Okay, what do you guys think? What should we do next to start simplifying this? Right, this has to somehow simplify all the way down to x. What should we do next? Who's got an idea? After you guys give me at least a couple of ideas that I don't like, I'll tell you what I would do that makes this a little bit easier. Can I cancel them out?
Like
the fractions? Inside of the fractions? No. So Margot, here's the thing. You guys are going to be wrong a lot of times, and guessing is fine, because you know what happens, or what the other thing I'm trying to do here is when you get stuck and you look at something like this and you're like, I don't have any clue what to do on the test or quiz. What are you going to do? You're going to guess. And so at least what we can do here is when you shout out your guesses, I can talk about why they're not right. And when you get to that same situation later, at least you've crossed something off that you're like, maybe I won't do that next time because he's shown me why I can't ever do something like that. So this is still really productive. And I want to follow up. And when you say cancel that, I want to get into this and explain why maybe what you're suggesting either is a bad idea or something that just is something we just can't do. Right? This is productive. So let's elaborate here. When you say cancel this out, what do you...
Would it be possible to cancel out 5?
So you are talking about this 5 with this 5? Definitely not. Okay? So if we think about this in, if I simplify this, and when I say, if I think about a simpler version of this problem, where I've just replaced that 8x plus 5 over 5x minus 2 with the number 3. If I had something like this, can I do that? Definitely not, right? That's outside of the order of operations. We'd have to do everything in the numerator before we can do the division, right? So that's what you're kind of suggesting to do. John? Yeah, so you could distribute the 2 and the 5 into the numerators, right? And that would be okay. But I don't think is going to be the most effective route, but would not be incorrect. I want to be clear on that. I'll show you the shortcut that allows us to not even have to worry about doing that, though, right away. Of course. And John, the drawback of going that route is that afterwards, you're still going to need to make like a common denominator in both of the numerator and denominator to like add the fractions, and like it gets to be kind of messy. Here's what I would do. Is I'm going to multiply the top and bottom by 5x minus 2. Why in God's name did I choose to do that? Yes.
Cancel out the fraction.
Yeah. So when it distributes, it's going to distribute to these two places, and that denominator is going to cancel out. And that's going to cancel out, right? And it's okay to do that, to multiply by 5x over 2, or 5x minus 2 divided by 5x minus 2, because all I'm doing is multiplying by 1, really, right? And in one step, I got rid of the fractions inside of fractions. Which, boy, is that an improvement in terms of what to do next, right? Notice that I never had to worry about making a common denominator and adding fractions, which is also kind of a pain in the tuchus. I knocked that all out with one step, which is a pretty great shortcut. Does that feel okay here, my peeps? What should I do next? Should be easy from here. We want to distribute, right? Is that what you're whispering about in the back?
No, we're wrong.
No?
We were saying to cross out.
Well, you can't reduce here for the same reason that we couldn't reduce before, is because you're talking about dividing before you've added and subtracted, right? So let's do that. 16x plus 10 plus 25x minus 10 over 16x plus 25 minus 40x minus 16 . Okay. That all look okay to you guys? Something isn't working out here. Let's see. So those cancel out. I'm left with 41x in the numerator. And then I combine my like terms in the denominator. Five times. Oh, thank you. Yeah. That saves my bacon there. Thank you. Yes, sir.
Also, wouldn't it be plus 16?
Yeah, that'll do. Good gravy. Thank you for paying attention. Okay. So I have 41x over 41. And now everything works out. Whew! That makes me feel a lot better. I'm like, oh no, did I screw up this inverse? No, we did it right. I just can't multiply apparently today. It's the simple mistakes that get you guys. Does that feel okay? I'm going to skip doing the other direction because it's really the exact same problem. Just the numbers are going to be like different spots or whatever. But you do it the exact same way. Do you guys need to see it, or can we just do another one? Actually, we probably don't even have time to really even do another one, do we? We have like 4 minutes or something left in class. So let's just call it quits here. I'm exhausted. Are you exhausted?